In this lesson, we're going to go through the double angle identities. Now, in our previous lesson, we have discussed the compound angle identities or the addition formulas, which consist of finding the trigonometric lines of a plus b and a minus b. However, we're going to use the compound angle identities in order to prove the double angle identities here. Now, sine 2 theta is 2 sine theta cosine theta, and that is because if I were to go back to sine of a plus b, the compound angle identity of sine of a plus b is sine a cosine b plus cosine a sine b. However, over here we have sine of 2 theta or sine of 2a, doesn't really matter. So in the compound angle identity, if I were to set a equals to b, so if a is equal to b, in that case a plus b is equal to 2a. So in that case, so if a is equal to b, then we would have a sine of 2a equals to sine a cosine a plus cosine a sine a. So now for a equals to b, these two terms are in fact the same term, which would lead me back to 2 sine a cosine a. So that is why the double angle identity of sine is as follows. And similarly, if I were to determine the double angle identity of cosine 2 theta or cosine 2a, referring back to the compound angle identity of cosine, which is cosine a cosine b minus sine a sine b. So over here again, if I set a equals to b, then in that case I would in fact obtain cosine 2a equals to cosine a, which in fact leads to cosine squared a, minus sine a, which is sine squared a. So that is where the first double angle identity of cosine comes from. So it's from the compound angle identity of cosine by setting a equals to b. However, the other two versions of the double angle identity of cosine comes from this first one using the Pythagorean identity. Now we know that cosine squared a is 1 minus sine squared a, so that would in fact lead me to this third double angle identity of cosine. So replacing cosine by 1 minus sine squared a minus sine squared a again, that would leave me with 1 minus 2 sine squared a. And similarly, using the Pythagorean identity, we already know that sine squared a is also 1 minus cosine squared a. So replacing sine squared a in the double angle identity of cosine by 1 minus cosine squared. So that would in fact leave me with 2 cosine squared a minus 1. So these are in fact the justifications of the double angle identities of sine and cosine. However, the double angle identity of tan is in fact tan 2a is 2 tan a over 1 minus tan squared, and that also comes from the compound angle identity of tan. We already know that tan of a plus b is tan a plus tan b over 1 minus tan a tan b. Again, setting a equals to b. So if a is equals to b, that would in fact leave me with tan 2a equals tan a plus tan a at the numerator, that's 2 tan a, over tan a times tan a, so that's 1 minus tan squared a. So this is in fact where the double angle identity of tan also comes from. Now in the following, we're going to apply these double angle identities into examples. So starting with the first example, if we're given sine a equals to 2 over 5, where a is an acute angle. A being an acute angle, it means that a is in fact in quadrant 1 on the unit circle. So we need to evaluate sine 2a and cosine 4a. So now sine 2a, sine has only one double angle identity, which is 2 sine a cosine a. So I already have sine a given. I need to determine cosine a. So cosine squared a using the the Pythagorean identity is 1 minus sine squared a. So that's 1 minus 4 out of 25. So cosine squared a is in fact 21 over 25. Now a being in quadrant 1, it means that cosine is positive. So over here cosine a, it would in fact be the square root of 21 over 5. So since a is acute, so a being acute, it means that cosine of a is positive. Okay, so now I can find sine 2a, which is 2 times sine a, which is 2 over 5, and cosine a, which is square root of 21 over 5. So that leaves me with 4 square root of 21 over 25 for sine 2a. Now, if I were to find cosine 4a, now cosine 4a, now 4a is in fact the double of 2a. Now we already know that cosine 2a is 1 minus 2 sine squared a. Setting lowercase a here in the identity to be equals to 2 times capital A. That would in fact, 2 times A would in fact give me 4 times capital A. So that would in fact leave me, according to the identity, with 1 minus 2 sine squared of 2a, which we have already found. Now I've decided to use this double angle identity of cosine, the one in terms of sine squared. It is because I have already found sine of 2a. If I were, for example, to use the original one, over here, I have sine squared of 2a. I would then need to find cosine squared of 2a. So I would need to find cosine 2a. But however, since I already have an identity in terms of sine only, so I would go for that one since I already have sine. So I would not really have to do extra work. So over here, according to the double angle identity of cosine in terms of sine, cosine 4a is in fact 1 minus 2 sine squared of 2a. So replacing here, over here that's 2 times sine squared a, this is 16, times 21 over 25 squared, which is 625. So reducing to the same denominator, that would in fact give me negative 47 over 625. Moving forward to the second example, we have tan a to be equal to 4 over 3, where a is between 0 and pi over 2. That is also in quadrant 1, and I need to evaluate tan 2a. Now, that is very straightforward. All we have to do is just use the double angle identity of tan. So tan 2a would in fact be 2 tan a over 1 minus tan squared a. So I already have tan a, so all I have to do is just replace and simplify. So that would be 2 times 4 over 3 divided by 1 minus 16 out of 9. So at the numerator, I do have an 8 over 3. At the denominator, replacing over here, reducing the same denominator, 9 minus 16, that's a negative 7 out of 9. So that's a negative 9 out of 7, dividing by a fraction. So we multiply by its reciprocal. So we could over here simplify this into negative 24 over 7. So that is tan 2a given tan a in this quadrant. In this third example, we are asked to show that sine 3a is equal to 3 sine a minus 4 sine cubed a. Now, in order to prove this identity, usually whenever we have an identity to prove, we either start with the left-hand side and try to reach the right-hand side, or start with the right-hand side and try to reach the left-hand side, or start with each side separately and try to prove that each side is equal to the same quantity. However, over here, there's nothing much I can do on the right-hand side, so this is why I would start with the left-hand side and try to reach the right-hand side. So sine 3a, since I already know the compound angle identities and the double angle identities of sine, now in this case, I would think of splitting 3a into 2a plus a. So over here, sine of 2a plus a, we could use the compound angle identity of sine. So sine of a plus b, that would in fact be applying the compound angle identity. That's sine 2a cosine a plus sine a cosine 2a. That is according to the compound angle identity of sine. Now, in order to reach the right-hand side, which is all in terms of sine A, I would in fact need to get rid of cosine A and the double angle and the trigonometric lines in terms of the double angle. So first I will start by applying the double angle identities of sine and cosine in order to get rid of sine 2a and cosine 2a. Sine 2a we already know is 2 sine a cosine a times cosine a again, that would in fact leave me with cosine squared a, plus sine a into. Now cosine 2a, I already have 3 possible identities for it. Since I want the right hand side to be all in terms of sine a, I would go for the double angle identity in terms of sine, which is 1 minus 2 sine squared a. However, you'd notice that this term is now all in terms of sine a. Over here, I already have a sine a here, but I still have a cosine squared. But that is not a problem because according to the Pythagorean identity, now cosine squared is in fact 1 minus sine squared a. Expanding here, that would give me sine a minus 2 sine cubed a. Now expanding here and simplify, we would obtain 2 sine a minus 2 sine cubed a plus sine a again minus 2 sine cubed a. Now rearranging similar terms, you'd notice that we end up with the right hand side that we are required to prove. 2 sine a, and sine a is 3 sine a minus 4 sine cubed a, and that is what was required to prove here. Now in this fourth example, we have 4 minus 2 cosine squared a, which I need to write in terms of cosine 2a. Now referring back to the double angle identity of cosine. Now the double angle identity of cosine, we already have 3 of them. Okay, so now over here, since I want 4 minus 2 cosine squared a to be written in terms of cosine 2a, then I would go for the double angle identity of cosine that is in terms of cosine squared, which is 2 cosine squared a minus 1. Now over here, all I have to do is just solve for cosine squared a in terms of cosine 2a and replace in this given expression. So first I start by adding 1 to both sides. So that's 2 cosine squared a. And then solving for cosine squared a, that would give me half into cosine 2a plus 1. Now replacing cosine squared a here by this identity. So that's 4 minus 2 into, that's a half times cosine 2a plus 1. 2 times half, that is a 1. So that's 4 minus into cosine 2a plus 1. Expanding the negative, that's 4 minus cosine 2a minus 1, which leaves me with 3 minus cosine 2a. So whenever you have cosine squared or sine squared that you need to write in terms of cosine 2a, what you could do is just the same way I did here, is use the double angle identity of cosine in terms of cosine squared or sine squared, and then solve for cosine squared or sine squared in terms of cosine 2a, and then replace. Now this is the double angle identity of cosine. This is also known as the half angle identity of cosine, which is in fact is a result or a consequence of the double identity of the double angle identity anyway.